Just to give a little bit more of an introduction to Novolon, what we are is we are about a 3,000 person company headquartered just down the road. We've been around for about 20 years, and primarily we served the health insurance sector. But over the last 5 to 10 years, we've much more diversified into the provider space as well as the pharma and the specialty pharma sectors. So what this has done for us is actually given us a very wide set of data streams that we can actually use for a lot of these problems. So our team, the AI team at Novolon, we uniquely, I like to describe this as a kind of a special ops team where we find projects that are out there, we try to solve them quickly, and then move on to the next one. So we get very, very diverse projects, and the academic collaborations that we've had with University of Maryland and NJIT have been absolutely pivotal to this. So I would encourage anybody to discuss with the companies here or the academics here if you're a company as well. So to start with Forbes, one of the worst offenders for headlines, they have a title here that says, "Will artificial intelligence soon tell us how to live?" Question headlines are almost always answered with a no. But the reason why we've seen health be so evasive towards AI is, in all honesty, it is one of the most difficult fields to apply AI to of any field. A lot of the times we hear explainability as being part of that, but there's all sorts of reasons. There's a variability of data. So we see medical records, even today, are still very poorly standardized. Electronic health records, even those today, are still very, very segregated in how they are structured and how they are updated. And there's a lot of effort to improve this in the health sector, but currently it's still a continuing problem. Data access, HIPAA laws are making things very difficult, but obviously for good reason, as well as being able to have academics, for example, have good access to data is something that we are trying the government's actually doing a much better job now than ever before. We also see personal information risks, and that goes in the same vein, as well as changing government policies. So this is a big one because, of course, whenever you train a machine learning or a deep learning algorithm, you train it on past results. Now, for health, a lot of the times there are changes on, for example, how diabetes is defined. So if we change that going forward, the model itself needs to be updated again, and it's no longer relevant. So it makes health algorithms very, very difficult on this front. And the last one doesn't apply to everything in health, but it's definitely one of the most visible: high punishment for error. And this is where that explainability comes in, is whenever you have that, you do need that explainability. So algorithms like what you see in the Netflix ranking algorithm or text message suggestions or Google ranking, they don't require explanations because the punishment for error is actually very low. But here we have to account for that. So the first place I always look, I'm an engineer at heart, is to see what data we have available, and that's the data scientist way as well. When we're looking at data sources for large products in the health space, we like to look at what the data is available for every single patient possible. Things like the smartwatches, they're only on about 10% of people, but about 100% of people have claims data, medical records, or these JSON forms that are described on the bottom left. There are a lot of different data available, as you can see. I can spend an hour looking at this chart and trying to interpret everything that's there. But these four are the biggest continuous data feeds that we see a lot of health decisions are continually made on a daily basis. So claims data is really the language of health insurance companies and CMS, which define alphanumeric codes describing what's wrong with a patient, as well as lab codes and different charging codes for reimbursement. XML and JSON forms are often structured forms used for either nursing assessments or doing an assessment in somebody's home, as well as medical records, which I said already come in a lot of different shapes and sizes. These are still, a lot of the times today we see these as just straight up PDFs with lots of handwriting on them, which makes it very tough for computers to interpret. So today we have a very, very large optical character recognition operation where we go through about 1 million records a year. It's a lot of pages. HL7 FHIR is a very new concept. It's an API-based form of exchanging health information. It is not implemented today. However, a lot of the hospitals out there and insurance companies are starting to structure themselves to be able to take in this data and quickly flip over to this system, and I'll cover it in a little bit more. So when we look at the different problems that we can approach, we look for situations where we can rank opportunities, and I described Google and Netflix as two of those examples. So there's a lot of interest in finding patients or providers who are very risky, maybe providers who are distributing lots of opioids. When there are a large number of variables, it's a very good use case for a machine learning or an AI product, or if probability is important. So financial estimates, or if you're looking for a thresholding. And I say financial estimates because in options trading, we multiply the probability of an option expiring at a price times the value of it once it expires at that price. And you can do that for the costly events to find patients that are very costly versus not costly. And so finding patients over a risk threshold as well. So if we find that patients are beyond a risk of falling, we might hand them a pamphlet or something like that. So I'm going to go through a number of use cases today because to me that feels like where the most grit is, and I like to see what the real things are. So here we have a medical image. This was done by ChexNet. It's a Stanford group, which is a really unique product because they implemented a radiology detection algorithm, which didn't just say whether the radiology image did or did not have a condition implied. It also showed a heat map showing where the focus was that was recognizing that. IDXDR is also one that is FDA approved. It's one of the first FDA-approved neural networks, mid-2018. It can detect diabetic retinopathy, and it's used as a screening tool. So if you're detected as having it, it will divert you to the appropriate provider. And this does not need a clinician to actually operate it, which is why it's such a big deal. One of the ones that Inovalon's really excited about to work on is specifically predictions with claims. So these alphanumeric categorical codes are very useful for predicting different things that might happen to a patient. So we use this for predicting things like falls or emergency readmissions into a hospital or pressure ulcers. The list goes on and on. We built this framework to be able to model and predict nearly any event at any future specified period. And this uses, for anybody who's into deep learning a lot, this uses a very unique claims embedding that we actually built that's able to semantically represent any different claims code in an embedding. This is an example of what Google is actually currently working on. I'm not paid by Google, by the way, but I like to be aware of the really interesting projects that are going on. So Google's been quietly working on this for about a year and a half now, where they published a paper about it and ultimately applied for a patent about 2 or 3 months ago that includes visual images, which uses FHIR or FHIR data, which I was discussing earlier, at the provider location. So because we are, our company is mostly insurance company focused, the claims is where we typically operate. We've also built frameworks to do this, and other companies have as well. But it's where we see really Google putting the most amount of effort. They're kind of waiting for when health data is much more well structured so that they can go forward with offering a tool in the provider space for monitoring patient health. Patient outreach is a really big one as well. So if you are a patient and you have a condition and you are not likely to see your doctor without somebody pushing you to, there's a big incentive for insurance companies as well as providers to figure out the best way to contact you and talk to you about how to see your doctor or the easiest way to get you to a doctor. There's a lot of examples of programs of literally paying for Uber to pull patients to a doctor so that they can get that risk taken care of. And there's a lot of different ways to do this. Of course, older populations might not reply via the most technical savvy methods, but we're able to do this in a lot of different ways. Gap detection is a big one as well. There's a high incentive in the insurance sector to look for conditions that are not identified as present. So this is actually machine learning software that will actually look for a patient's probability of vascular disease. using different using claims data. So given that claims data, output the probability of a specified gap. And so you can see here, there's a lot of different indicators like arterial studies. On the bottom, we see things like debride nail, which is a decaying nail, toenail, which results from poor blood circulation. And so these are the top indicators. We are able to get this transparency for all of these models. We see a lot of insurance companies starting to do more work like this, as well as provider interest in things like this. I did a presentation yesterday about medical record review. This was actually the reason for the inception of the AI team at Inovalon, was to try to be able to mine medical records such that if you provide us with a medical record, we can return back what the patient's conditions are. We do use machine learning and deep learning to do this today, depending on the line of business. So here I actually show a graph where we have a 260-page document where through our collaboration with the University of Maryland, we were able to build a detector for vascular disease, but we simultaneously run this for all diseases at the same time. So you can see there's about 2 locations in the chart where we could detect with a high confidence that vascular disease was mentioned in this completely unstructured PDF medical record. And we offer a number of other features in that as well, which is actually a product for our company today. So the last thing I want to leave with here is really just a keys to success on what we've seen really helps when we're building production level machine learning and deep learning capabilities. And that's first transparency, being able to describe what the reasons for the model making the decisions is. It doesn't always have to be in deployment if it's not needed in deployment, but at least in training, all of our models actually get looked over by medical doctors before they leave our desks. And this is definitely a mandatory process, so getting that transparency even at the point of training is definitely very important. Time to market, one of the things we see is that you can spend a lot of time making a model that's very complex and get that extra marginal 1 to 5% gain out, or you can keep a model very simple and have it perform very well regardless of that 1% deficiency and get it to the market much sooner. So we see that as really valuable for keeping our team going. Or failing fast, of course, if you have a model that can't predict something. We have come across models where we put everything in and we aren't able to predict it and we just move on. So communication, I think in specifically the health space, we see that communication between clinicians and data scientists is something that hasn't thoroughly been explored until the last few years. And so being able to work between these 2 disciplines where there's a lifetime career essentially involved in specializing in both of them is really important to have as much communication between the engineers or the data scientists and the actual people with the problems that are trying to be solved. And then finally, just maintenance. I hit on this a little bit earlier, but being able to watch the government policies as they change, which is really important for the health sector. If it changes and your model is now defunct, or you don't have new incoming data to be able to accommodate that, it can be damaging to a model already in production. Online training or learning as you go is something that's talked about a lot, but it's actually fairly dangerous because if a model is fed poor data, it could result in poor predictions without that being monitored. And that's also true for maintenance, also includes scalability as well as dependencies. So taking in multiple data sources can be dangerous when making a decision if one of those data sources is no longer available in the future, which is why over the last few examples I actually gave only one input as the input to every single output. So this is something that we see as definitely key. And that's all I got. So thank you so much for everyone. I think we might have a little bit of time for a question.
Would you take a question if there is one?
Yeah.
All right, one question.
Yes. Yeah, this is Mohammed Bajwa from UMUC. I think we had a discussion yesterday inside the classroom and outside the classroom, so I'll not repeat those questions. My question is now that EHR collects tons of data on cardiology, radiology, pathology, and all that kind of thing. Have you developed any techniques for analytics of that data?
Yeah, so we do have a number of techniques for breaking down EHRs. In the language processing algorithm I showed, we don't do it by default just because so many of the records that we still see today are PDFs. But there are definitely a rising number of use cases where there's interest in looking in the records for what's available and using that for tracing things. For example, we recently have a new, the head of the bioinformatics at Harvard, Zach Kahani, he recently joined our board of directors. He built his career in trying to cross genomics data with EHRs specifically and mining those EHRs for specific locations and conditions in those locations. He's definitely very interested in doing a lot more on that. We do have a product today which parses and distributes that data, but what we see is that one of the big problems is that even the largest EHR vendor only covers about 30% of the market. So there's a lot of variability in what these EHRs look like, but we are able to accommodate that to a moderate degree. It's definitely a big point of improvement in the whole health sector, though, that needs to be addressed.
Thank you.
Thank you.